In order to enable a submarine to launch ballistic missiles from 1,000 feet under the water, the missiles would have to be carried in capsules. The capsules would have double walls and would have enough flotation to carry the missile and the capsule to the surface for launch. At the back end of the capsule would be fins or vanes to make sure the capsule floats in an upright position, so the missile can be launched when the capsule reaches the surface. Releasing the missiles from depth provides greater protection for the submarine. When the capsule reaches the surface, it would be undesirable for it to broach the surface, to explode out of the water and come crashing back down. Therefore, a parachute might be fitted to slow it down so it bobs to a stop at the surface. When it reaches the surface, the front end of the capsule, the cap of it, would be blown off, and then the missile will be launched the same way a missile is launched from a submarine. There'd be a charge of water, and an explosive or deflagrating charge would detonate, vaporize the water, turn it into steam, launch the missile from the tube, and then the missile's rocket motors would start, and the missile would go on its way. It would be necessary to have a communications link between the submarine and the missile through the capsule, so the submarine can tell the missile its current location and direct it how to target and release its warheads. The Trident missiles on submarines are a little over 40 feet long, 6 feet in diameter. By laying the missile on its side, a missile of over 50-foot length could be built. That allows for a bigger motor, larger fuel, longer range, and a more capable missile. Laying missiles on their side means they have to be specifically designed for that form of storage. Otherwise, components can be overstressed and can possibly be deformed. The submarine would be built with an inner pressure hull of maybe 40 feet in diameter and 600 feet long, about the size of an Ohio-class submarine, or maybe a little bit larger. Around that inner pressure hull would be a shell wall of maybe 60 feet in diameter. The capsules would be placed into indentations, sponsons, in the shell wall. In order to accommodate a missile of over 50-foot length with its capsule, the entire sponson might have to be up to 120 feet long. All the curves leading into it have to be slowly and smoothly varying so that when the door is opened, it doesn't produce excessive hydrodynamic noise. The door also has to be designed to reduce and maintain a low level of hydrodynamic noise. If the shell wall attempted to span the entire 60 feet, it would have to be extremely heavy. All of the forces would be concentrated at the ends, and that would require a very thick piece of metal. But if the space between the shell wall and the inner pressure hull is allowed to flood with seawater and the pressure equilibrates, the shell wall can be built with much lighter construction. It can have an inner and an outer skin of metal, and then between it would be framing. And the framing would subdivide so that the distances spanned by the inner and outer walls would allow for relatively thin, maybe inch-thick plating. The shell wall would be divided into 10 by 10 foot sections. That way, if the shell wall is breached, only that 10 by 10 foot section would flood and not the entirety of the shell wall. The shell wall, its plating, and the spacing would be designed to try to attain neutral buoyancy. Seawater weighs about 64 pounds per cubic foot. And the goal would be to try to get it as close to neutral buoyancy as possible, because the whole submarine has to achieve neutral buoyancy. Between the pressure hull and the shell wall, there would be hollow steel tubes for bracing. The tubes are made hollow, again, to try to achieve neutral or even slightly positive buoyancy. At 1,200 feet, the pressure is about 76,000 pounds per square foot, 550 pounds per square inch. Steels can easily resist over 100,000 pounds per square inch. So you can have a steel wall which is thin enough that it still maintains buoyancy, while also avoiding problems of things like fatigue and buckling. The tubes would be connected like a child's connector set. In the tubes would be walls, and the walls are there to, again, prevent flooding. If the tube is broken at any point, only that section will flood and not the entirety of the tube structure. The entirety of the space between the pressure hull and the shell wall would be aluminized, and that would avoid corrosion. You'd actually spray aluminum onto it, which is fairly expensive, but does a good job of preventing corrosion. None of it's going to be seen, so it doesn't matter that it's nice and shiny. During operations, some kind of biocide could be added to the seawater to prevent marine growths from growing inside that water. The sail would have to extend from the pressure hull up through the shell wall, and then would have to extend enough above the shell wall to mount the forward hydroplanes and have them function. The entire submarine could weigh twice as much as an Ohio-class submarine, going from 18,000 tons to 36,000 tons. A lot of that weight would be the seawater that you're shipping around between the pressure hull and the shell wall. There is an equation called the Admiralty formula for estimating power of ships. And what it basically says that the power required goes as the 2/3 of the displacement. So if you double the displacement, you square that, you get 4, take the cube root, and it's 1.6. So the reactors would have to be 1.6 times as powerful. The propeller would have to be 1.6 times the area, or 1.3 times the diameter, and all the other control surfaces, the forward hydroplanes, the rear hydroplanes, vertical stabilizer at the back of the submarine, and all of them would also have to be built in a much larger form. A submarine that is 600 feet long, or maybe a little bit longer than that, you might be able to mount 2 rows of sponsons. With a 40-plus foot pressure hull and a 60-foot diameter shell wall, you might be able to mount 8 sponsons per row, with 2 rows that provides a total of 16 missiles. When the missiles float to the surface, they can actually wait for a while before they launch, and that gives the submarine a chance to go somewhere else, so that when the missiles are launched, it doesn't indicate the position of the submarine. The submarine is larger, more expensive, but it enables the submarine to launch missiles at depth without having to approach the surface, which makes the submarine more difficult to detect and better able to survive.